All right, let's talk about pumps. You ever look at a big, powerful motor on a pumping system and just wonder, where does all that horsepower actually go? Well, today we're going to pull back the curtain and dive into the real power behind moving water. We're going to break down the three distinct types of horsepower you'll find in any pumping system.
So here's the central question, right? It's a classic engineering puzzle. You've got this beefy 10 horsepower motor, but the actual work getting done, the amount of water it's moving, is way less than that. Now, this isn't some kind of defect or a broken part. It's just physics. And by the time we're done here, you're going to know exactly why this happens and where all that lost power really goes.
Okay, so to figure out where the power disappears, we first have to define the job we're actually trying to do. This is our baseline, our starting point, and it's called water horsepower. Just think of this as the pure theoretical work that we want to accomplish. So, water horsepower. It's a measure of the energy that the water itself is actually receiving from the pump. In a perfect world with no friction, no losses, this would be the only number that mattered. It is the true, useful output of the entire system. It's the work that actually gets done. This little formula here gives us our ideal scenario. Water horsepower is the absolute theoretical minimum power you'd need, but that's assuming a flawless, 100% efficient system, which, spoiler, doesn't exist. You can see it's calculated from two really key things: how much water you want to move, which is your flow rate, or Q, and how high you need to lift it, which is known as the total dynamic head, or TDH.
Right, but like I said, we don't live in that perfect world. The pump itself is not 100% efficient. So to get the water horsepower we actually want, we have to pay a price. You can think of it as an inefficiency tax. And this brings us to our second concept, brake horsepower. Brake horsepower is the power that the motor has to physically deliver to the pump's shaft just to get it spinning and doing its thing. So notice the shift here. This isn't the power going into the water anymore. This is the power going into the pump itself. So why is this number always bigger? Well, because the pump itself has all these internal losses. As water is churning around inside, energy is just getting lost to friction against the casing, to turbulence, and it's even generating heat. This inefficiency is captured by that little symbol, EP, for pump efficiency. The absolute key takeaway here is this: you always have to put more power into the pump than you're going to get out as moving water. But hold on, we're not done yet. The pump needs power, sure, but where's it coming from? It's coming from a motor. And guess what? That motor isn't perfectly efficient either. This leads us to our final and our largest horsepower value, motor horsepower. Motor horsepower is that number you actually see stamped on the nameplate on the side of the motor. It represents the total electrical power you are pulling from the wall, from the grid, to make this whole thing run. This is the true input for the entire system. And just like the pump, the motor has its own set of losses. You've got electrical resistance in the copper windings, you've got friction in the bearings, all of it wasting energy. This is measured by the motor efficiency, or eta-M. So to deliver the brake horsepower the pump is demanding, the motor has to draw an even greater amount of electrical power to overcome its own internal inefficiencies. Okay, so let's put this all together and look at the complete power chain. Think of it like a relay race where energy is getting handed off from one component to the next, and a little bit gets dropped at every handoff. This chart tells the entire story in one simple picture. You start with the big bar on the left, a large amount of motor horsepower. That's your total electrical input. Then, some of that power is lost as heat and friction inside the motor, which leaves you with the smaller, middle bar, the brake horsepower at the pump shaft. And then more energy is lost to all those inefficiencies inside the pump, leaving you with the smallest bar of all, the water horsepower, which is the actual useful work that's getting done. And this table just lays out that whole energy conversion process perfectly. You start at the bottom with the system input, your motor horsepower. Factor in the motor's inefficiency, and you get the brake horsepower that's delivered to the pump. Then you factor in the pump's inefficiency, and you're finally left with the useful output, water horsepower. The hierarchy is always crystal clear. Motor HP is bigger than brake HP, which is always bigger than water HP. No exceptions. So why does any of this actually matter? Well, it's simple. Every single one of those drops in horsepower from one stage to the next represents wasted energy. And wasted energy costs real money. This brings us to what is probably the single most important metric for understanding your real operating costs, something called wire-to-water efficiency. This number tells you, bottom line, how good your entire system is at turning the electricity you pay for, the wire, into the work you actually want done, the water.
And calculating it is actually pretty straightforward. You just multiply the pump efficiency by the motor efficiency, boom. Or you can think about it another way, it's just the ratio of the useful work you get out, that's your water horsepower, to the total energy you put in, your motor horsepower. This one single percentage is really the key to your electricity bill.
Let's just visualize this for a second. Let's say your system has a total wire-to-water efficiency of 50%, which, believe me, is not uncommon at all. This chart shows you what's really happening. Fully half, of the energy you're consuming is doing useful work. And the other half, it's literally just being wasted. It's turning into heat and noise. Now let's put that in dollars and cents because this is where it really hits home. If your total system efficiency is 50%, that means for every single $100 you spend on electricity to run that pump, 50 of those dollars are effectively being thrown straight into the trash. They're just being converted into useless heat and friction. Only $50 are actually doing the job you hired that pump to do. So, there you have it. We've solved the puzzle of the 10-horsepower motor. The power isn't just vanishing, it's being converted and, lost in each step of this chain. Now that you understand this whole flow from the wire to the water, it kind of leaves you with one last thought, doesn't it? Think about all the other systems all around you, your car, your appliances, all your electronics. How much of the energy that we use every single day is actually doing useful work, and how much of it is just lost?